The physical properties of alkanes are dictated by the fact that these molecules are what we call nonpolar. They have no distinct regions of positive and negative charge. Well, two questions about that. One is, why not? And the second is, what does it matter? Well, the why not question is answered easily. Alkanes only have carbon, and carbon, hydrogen, single bonds. These bonds exist because these atoms are sharing a pair of electrons. Let me just put a pair of dots in there. Because there's no difference in electronegativity between two carbon atoms, or a carbon and a hydrogen, those elements have almost identical electronegativities. Those electron pairs are shared equally by the two atoms. They're not shifted in one direction or the other, and therefore there's no regions of excess electron density, which would be negative charge, or deficiency in electrons, which would make positive charge. So because the atoms in alkanes all have essentially identical electronegativities, the electron pairs in the bonds are all shared equally, and there's no uneven distribution of electron density to cause negative and positive charges. So alkanes are nonpolar because all the atoms have about the same electronegativity. The second question is, well, why does that matter? Well, it matters because the forces between molecules, the attractions that molecules have for each other, is based on attractions between positive and negative charges. So for alkanes, you'd say, well, there are no attractions between those alkane molecules. And you'd almost be right. Not quite. There are very weak attractions between alkane molecules due to forces called London dispersion forces, or also known as van der Waals forces. And these forces are attractions that are based on fleeting, changing existence of very small positive and negative charges in the specific alkane molecule. And so molecules are attracted to each other because there are these brief, weak charges. Because they're brief and weak charges, the attractions are very small. And as a result, these molecules are not held together very strongly, which dictates alkane physical properties that we're talking about. Which ones? Well, these molecules have low boiling points and low melting points. Think about it. The boiling point is where there's enough energy supplied by heat to separate the molecules from each other as liquid to become gas. It takes energy to separate those molecules, and the energy it takes is dependent on how strong the forces are that are holding those molecules together. Because there are only very weak forces holding the molecules of alkanes together, the boiling points are low because it doesn't take much energy to separate them. The same argument goes for melting points. Solids exist because the molecules are held firmly in place by attractive forces. When these attractive forces are very weak, they're easily broken at low temperatures, which means the melting points of alkanes occur at very low temperatures relative to other kinds of molecules. There's another phenomenon about physical properties that's important to discuss relating to the fact that these molecules are nonpolar. Alkanes are essentially insoluble in water and have very limited solubility in other polar solvents. What we're saying here is, when placed together with a polar substance like water, alkanes would rather be together, and water molecules would rather be together, than mixed together with each other. So they're insoluble. And this is again a phenomenon that results because alkanes have very small fleeting charges at most within the molecules, and therefore have very weak attractive forces toward positive and negative charge. Okay, these are the facts. Let me give you a brief explanation that helps us understand the physical aspects of what I've just been talking about. Let's say that an alkane molecule is represented by this skinny oval, and we've got two alkane molecules here. Because these molecules have fleeting, tiny charges at most within the molecular structure, the attractions between these molecules are very weak because the charges are very weak. Boiling points of larger molecules tend to be higher than boiling points of smaller molecules. Why is that? Well, it follows from the same model. Take a look. When we have two long molecules represented by these long skinny ovals, we can have a number of these London dispersion forces causing weak attractions throughout the molecule. And these weak attractions add up to be much more when there's more atoms to be attracting to each other than in the small molecules. So larger molecules have greater attractions and higher boiling points and melting points. So there's a strong correlation between molecular size and boiling points. And for alkanes, although all the boiling points and melting points tend to be on the low side compared to other molecules, there's a steady progression of higher melting points and higher boiling points as the molecules get larger. How about the solubility explanation? Well, take a look at this one. Take a look at two water molecules that are strongly attracted to each other. They're strongly attracted to each other because the negative and positive charges in this molecule are pretty large. There's a significant difference in electronegativity between hydrogen and oxygen. And the proton is so small that it doesn't accommodate that positive charge well. So there's a very strong attraction between the hydrogen of one molecule and the oxygen of another. This results in very high boiling point for water relative to its size. Take a look what happens if we try to dissolve an alkane molecule in water. If we dissolve an alkane molecule in water with these very small weak charges, it separates these molecules. It's dissolving in water, so the molecules of water have to split apart. And as it separates molecules, it breaks very strong bonds holding the molecules of water together and replaces them with very weak bonds. The forces that exist between these tiny charges that are fluctuating in alkanes and the positive and negative charges of the water molecule. So it costs us a lot of energy. We're breaking strong bonds and making very weak ones. And as a result, energetically, it's more favorable if the nonpolar molecules all stay together and the polar molecules all stay together. And that's why you've heard this phrase, like dissolves like. Nonpolar compounds like to be together, polar compounds like to be together. And in this particular case, that explains why alkanes are insoluble in water and have very limited solubility in other polar solvents.